In this video, we explore the critical features that ensure safer journeys for all road users: skid resistance, surface texture depth, and drainage efficiency. This is our group team member, Daniel, Deborah Deirdre, Mohammed Zuluzny, Noor Farhana and Zaid Haritza. Road safety is very important, especially in busy places like university campuses. The condition of the road surface affects how safe it is to drive. Skid resistance helps cars avoid slipping, surface texture gives tires better grip and lets water flow away, and good drainage prevents water from collecting on the road. Together, these features make driving safer and reduce the risk of accidents.
The apparatus using in sand patch method are spreading tool, ruler, brush, sand, sample cylinder and water. Sand patch rough surface dry condition. Step 1. Find a dry and clean surface. Step 2. Measure 20 milliliters of sand. Step 3. Pour into the pavement surface. Step 4. Flatten the heap of sand following counterclockwise. Step 5. Record the diameter 3 times to get average. Step 6. Clean the pavement and put back the sand use in its special jar. Sand patch rough surface wet condition. Step 1. Find a dry and clean surface. Step 2. Pour water onto the surface of the road. Step 3. Measure 20 milliliters of sand. Step 4. Pour into the pavement surface. Step 5. Flatten the heap of sand following counterclockwise. Step 6. Record the diameter 3 times to get average. Step 7. Clean the pavement and put back the sand use in its special jar. Repeat step 1 until 6 for sand patch, medium surface dry condition. Repeat step 1 until 6 for sand patch, smooth surface dry condition. Repeat step 1 until 6 for sand patch, smooth surface dry condition.
The results showed clear differences between the 3 surfaces. The rough pavement had the highest texture depth, with values of 0.193 cm in dry conditions and 0.187 cm in wet conditions. The cement surface showed moderate texture depth, around 0.054 cm dry and 0.053 cm wet. Finally, the smooth tile surface had the lowest values, approximately 0.049 cm dry and 0.048 cm wet. From these results, we can see that rough surfaces provide the greatest texture depth, which improves skid resistance and drainage. Medium surfaces, such as cement, offer moderate friction suitable for pedestrian or low-speed traffic areas. Smooth surfaces, like tiles, have very low texture depth, which increases the risk of slipperiness, especially when wet. Across all surfaces, moisture slightly reduced texture depth, but the differences were small. The findings highlight an inverse relationship between surface smoothness and texture depth. Rougher surfaces are safer for vehicles because they provide better friction and drainage. Smoother surfaces may require additional treatments, such as anti-slip coatings, to ensure safety. Overall, the sand patch test confirms the importance of surface texture in highway design and maintenance, directly influencing skid resistance, drainage efficiency, and user safety. The objective of skid resistance ensures road safety by providing enough friction between tires and the road. This helps drivers brake, steer, and stay in control, especially on wet surfaces where traction is reduced. Its main goal is to prevent skidding, loss of control, collisions, and rollovers by giving vehicles the grip they need for safe maneuvers. This testing was conducted using the skid resistance tester. The testing was begin with rough surface. Clean the area to be tested using a brush. Set the base level by mean of the spirit level and 3 leveling screws on the base frame. Adjust the base until the bubble center in the eye. Adjust the pendulum height so it swings freely and reaches 0 on the scale. If it does not, record it as an apparatus error. Adjust the height of the pendulum by lowering the arm until the slider just touches the surface over the precise distance in scale rule which is placed alongside. Release the pendulum arm and record the reading. Make 3 swing and record the mean of successive reading. Repeat step 4 by wetting the surface. And record the data for 3 swing. Steps 1 to 5 are repeated for medium and smooth surfaces. Steps 1 to 5 are repeated for medium and smooth surfaces. Steps 1 to 5 are repeated for medium and smooth surfaces. Steps 1 to 5 are repeated for medium and smooth surfaces. Steps 1 to 5 are repeated for medium and smooth surfaces. Steps 1 to 5 are repeated for medium and smooth surfaces. Steps 1 to 5 are repeated for medium and smooth surfaces. Steps 1 to 5 are repeated for medium and smooth surfaces. Resistance test. Measurements were conducted at 3 different locations representing rough, medium, and smooth surface conditions. At each location, 3 readings were taken under both wet and dry conditions, and the average value was calculated to ensure data reliability and consistency. These average readings are used for further analysis and discussion. Based on the results, location 1 with a rough surface recorded the highest skid resistance, with an average value of 116 under wet conditions and 127 under dry conditions. Location 2 with a medium surface showed moderate skid resistance values of 61 wet and 74 dry. Meanwhile, location 3 with a smooth surface recorded the lowest skid resistance, with 40 wet and 52 dry. According to the JKR standard, the minimum acceptable skid resistance value is 46. From the results, both rough and medium surfaces comfortably exceed this requirement under all conditions. However, the smooth surface fails to meet the JKR requirement under wet conditions, indicating a higher risk of skidding, especially during rainfall. To maintain skid resistance in accordance with JKR standards, appropriate surface treatments can be applied. Chip seal is effective for significantly improving surface texture and skid resistance. Microsurfacing provides a uniform texture and restores friction performance. For localized defects, crack sealing helps prevent surface deterioration that may reduce skid resistance over time. These treatments are essential to ensure long-term road safety and compliance with JKR requirements.
In this part, we are going to show on how the outflow meter test works and what it is used for. And the objective of this test is to figure out how fast water flows out of the outflow meter. And basically, we measure how long it takes for a certain amount of water to exit, and then we can calculate the flow rate. So for this test, we'll be using 3 things: the outflow meter, a stopwatch, and water. In this part, we are going to show on how the outflow meter test works. And so before we actually start the outflow meter test, there are a couple of things that we have to set up. First thing we do is find a clean and dry surface. This is important because the outflow meter needs to sit flat and steady. And if the ground is wet, uneven, or dirty, it can mess with the stability and also affect the accuracy of the test. Once the surface is ready, then we can move on to setting up the equipment. We place the outflow meter on the flat surface, and then we add a 3 kilogram weight on both sides. The weights basically help with the whole setup from wobbling or shifting when we pour in the water, and that way everything stays stable and we get proper consistent flow readings. Now moving on to the next step, at this stage we fill the outflow meter with water. This is just to set the initial water level before we start timing the test. While pouring the water in, we make sure it reaches the correct starting level so that the results stay consistent for every trial. And once the meter is filled properly, we're ready to move on to the next step of the experiment. For this step, we pull the stopcock to let the water start flowing out of the meter. As soon as the water begins to drop, we start the stopwatch. The goal here is to time how long the water takes to reach the lowest mark on the scale. This timing is important because it's what we will be using later to calculate the flow rate. And once the water hits that lowest mark, we stop the timer and that completes this step. And then finally, all the recorded times are then listed in a table like this. Each row shows the surface texture we tested and the exact time it took for the water to flow out. And these times are what we will be using later to compare how different surfaces affect the flow rate. The previous steps were repeated on 2 other surfaces to make a comparison on different surface. Now let's look at the data we collected from the outflow meter test. For this experiment, the volume of water that we used was 400 milliliters, which is equal to 0.0004 cubic meters. To calculate the flow rate, we use the formula flow rate equals volume divided by the time taken. So based on the times recorded earlier, we get the following flow rates. For the smooth surface, the time was 20.8 seconds, giving a flow rate of about 0.00001923 cubic meters per second. For the medium texture, the time was 9.88 seconds, giving a flow rate of 0.00004049 cubic meters per second. For the rough surface, the time was 5.57 seconds, giving a flow rate of 0.00007181 cubic meters per second. And these numbers basically show how fast the water flowed on each surface texture. Now let's look at the data we collected from the outflow meter test. For this experiment, the volume of water that we used was 400 milliliters, which is equal to 0.00. Let's discuss what these results actually mean. First, the smooth surface had the slowest flow rate, and that's because the smoother texture created more friction and slowed the water down as it flowed. Next, the medium texture surface showed a faster flow rate. This surface reduced some of that friction so that the water was able to flow more easily compared to the smooth one. And finally, the rough surface had the fastest flow rate, and this means that the rough texture offered the least resistance to the water, which allowed it to move much quicker. So overall, as the surface gets rougher, the flow rate increases and the water moves faster. Let's discuss what these results actually mean. First, the smooth surface had the slowest flow rate, and that's because the smoother texture